Hello everyone. We are starting with our last chapter. Oh, getting finally there, right, towards the end. And that's chapter 8 on Laplace transforms. You might ask, what the hell is a Laplace? Well, that's the name of a guy. For those that speak French, they recognize, well, that's a French name, right? Laplace. And he was a French mathematician, and he also had contributed to this study of differential equations, as so many mathematicians, because it is such an important, I keep saying this, that this is the gateway, differential equations, the gateway to all advanced sciences. We have seen already some applications of it, and of course there are many, many more that we won't cover, but okay, so what is this Laplace transform? Before I can go there, I have to do a little review on improper integrals. Oh, you say, oh, okay, I remember that word. I have no clue anymore what that was. And I thought that. So you see, these things keep coming back, right, from calculus. So what was an improper integral? Well, what was a proper integral? A proper integral was an integral that was defined on an interval from a to b. But very often we would like to look at intervals that are infinite. So this is a proper integral. So what is an improper integral? I'm going to make it improper by putting here an infinity here. There are other reasons why an integral can be improper, but for us this is the only ones that we're going to be interested in. Okay? And for reasons that will become clear later, I'm going to always use t as my variable rather than x. Also because in applications, this is very often in physical applications, t is time. But it's also for other reasons that it's better to take t here. Okay, so what does this mean? Does this make sense? Well, yes, it is. By definition, it's the limit. So what we do is you replace this infinity by, I guess I lose capital T here, and then let capital T go to infinity. So we realize an improper integral always as an integral, as a limit of proper integrals. Because, why do we do that? Well, because here we know how to solve this using the fundamental theorem of calculus. We find an antiderivative, and then we plug in the endpoints. And then we have to take the limit. Now, of course, this limit cannot exist. It's probable that it's possible that this improper integral doesn't exist. We say that it diverges. And what we will see is very often it will diverge for certain values and will converge for other values. Okay, so keep that in mind. So technically, we have to take the two steps separately. So we have to do the antiderivative, plug in the endpoints, and then take the limit. And in general, one should do that because there are some small dangers by not doing that, especially when you would have not just one improper, if you would have two infinite endpoints. Okay. Now, what we will do is very often combine this in one single step. Okay. This is all that. It's just very, very quick review on improper integrals. And now I'm going to get right to the definition of the Laplace transform. So we have a function f. So f is a function, and it has to satisfy certain conditions that I'm again going to be a little bit loose with and not really pay too much attention of. But what we call, in particular, we assume that it is defined on the positive real axis. Okay, so. And we think of it as a function of time t, as I said. Although, I mean, I shouldn't say time t, of the variable t. Okay, so what is the Laplace transform? So the Laplace transform and since this is an important concept, it's used a lot in differential equations and so on, although we will not see much of it, we'll just touch upon the theory. There are several notations for that. So the first notation is just L of f. So we think of this as L from Laplace operating on f. It's an operator, as in fancy terminology. It will give me a new function. The idea is it's going to be a new function, but the variable will change here, and for a reason. So this will be, the variable here will be s. So I won't, let me not write it that. So don't think of this as L is the function, F is the variable. That's not what I mean, right? This is an operator. So in some sense I should make this a bit different boldface. I would have preferred to hear a bit boldface that you can see really it's not, this is not a function L. It is something that operates on F. Like another operation would be taking the reciprocal, or for instance taking the square of a function. That are operators on functions. So the result is again is a function. So this is a function in S. So the new variable will be S. And here's the definition. But we also sometimes indicate this by saying we will write this way by a double arrow here. I'm trying to make it look the same as in the textbook. And so F, what is F here? Well, as I said, it's going to be a function of S. So this is going to be F, right? F of S. That is, we also will denote it this way. I'm saying there's several notations here, okay? So what is this then? Well, by definition, so this is definition, this is going to be the following improper integral. Okay, here, this is, now let's look a little bit what is in there. Both S and T seem to be variables here, okay? But when we calculate this, as far as the integration is concerned, that is with respect to T. So as far as integration is concerned, S is a constant. Right? So what we need to do is find what we called earlier in an earlier session, we called that the partial antiderivative with respect to T of this function. Okay? Now notice that it is the original F, and then there's this one extra factor which is e to the minus st, and this is always the same factor. So this is the one that changes depending on what f's we plug in, and we get different outcomes, capital F's. Okay, if they exist, right? Of course, as I said, improper integrals might not exist, and in fact we will very often see that for certain s it exists and for other s it doesn't. Okay, so if this exists, then we call this the Laplace transform, and we denote this by this correspondence here. Little f corresponds to capital F, and the reason that it goes in both ways is something I will explain in the next video, next session. This will be part of the next section. Is that you can go back, so they determine each other. Okay, so. Now, let's look at the simplest example. So, we're going to look at examples and calculating these things. So, let's take f to be the constant function f1. So, the constant function. Okay, so this, if you want graphically, this is just a horizontal line, right? Okay, so what is L of 1? Well, we plug it into our formula, right? That is e minus st times f, but that's just 1, dt. Now, remember, s is a constant as far as the integration is concerned. So, we should, first and secondly, perhaps I should have said this first, we should convert it to a limit. But we're going to be lazy. And so what I'm going to do is I'm going to combine these two steps. I'm going to take the antiderivative and then plug in 0 and infinity, where plugging in infinity means really taking the limit for t going to infinity. Okay? So what is the antiderivative of e minus st? What is the antiderivative of et? Well, the antiderivative of et is et. What is the antiderivative of e5t? Remember, that is e5t divided by 5. Why do we have to divide by 5? Because if I take the derivative of this guy, the chain rule will give an extra 5, which I don't want. So I have to divide it out. This is the compensation rule. So here, S plays the same rule as 5 here. So we know that the antiderivative of E minus ST divided by minus S. Okay? Just treating minus S as a constant. And then we have to plug in 0 and infinity. And again, this is, so when we write this here, it gets a little bit less accurate because where are we plugging this in? Not in S, but in T. Okay? So let's see what happens then. So this is how we're gonna write it, but let's just for once spell it out a little bit more again, so that we don't make this, that we don't get confused. So we have, I'm writing my s's this way. So what is this for t going to infinity? Let's think about what happens. So this would be e minus, what is s times infinity? Now it depends a little bit on what s is, right? Multiplying a number with infinity, well, it's infinity. The only question is it minus infinity or positive infinity? So if s is positive, then I get here e to the minus infinity, right? There's a minus sign there, s is positive, and then infinity, and then divided by minus s. Now, it doesn't matter because this is 0. So we know that this is 0, right? This is 0. Okay? You with me? Okay. So what happens if I plug in, if s is negative? Oh, in that case, this becomes e to the positive infinity, because the negatives cancel each other out over minus s, and that is infinity. Now, if this is infinity, then we know this improper integral diverges. So it's only for positive s that we have something here. What do we have then? So, putting this a little bit in between, so we see here that if s is bigger than 0, what we get is, if I plug in, so remember, I'll do it one more time. So the plugging in would be this minus e to the, now what do I plug in here? There are two endpoints, right? I plugged in infinity, but I also have to plug in 0. If I plug in 0, what is that? In t. But of course, s times 0 is 0, so this e to the 0 over minus, should I plug in 0 here? No, this is s. The limit is for t going to these endpoints. This is, so if you want, this is really t equals infinity, and this is t equals 0. That's how you interpret these things. Okay? Let me not write it there because it's a little bit confusing perhaps if I write it there. So what is this now? Well, we just said that this is 0, so this whole thing is 0, so get 0 minus 1 over minus s. Well, that is just 1 over s. So I keep writing my s's in two different ways. I'll try to write it the same way. So what we showed that lambda of 1 is 1 over s. Or in our notation here with the arrows, to 1, that was the, if you start with 1 and you take the Laplace transform, you'll get 1 over s. It's kind of weird, right? You get start from something constant and you get all of a sudden something not constant. So this is really no longer integration anymore. This is different, right? Something else is happening here. And that's why it's a Laplace transform. That's why we only see it in a more advanced course. Okay. Now there's a whole table here of Laplace transforms. So here we see the first one that we have discovered here. That's our first discovery. We found this relationship here, that 1 corresponds to 1 over s. So there's many more, and we're going to use this table for other problems, but I want to do some more elementary calculations first, so that you get to see at least how these things work. So let's do the Laplace transforms for t. So the example now is, what is the Laplace transform of t? Okay, so the formula says it's from 0 to infinity, e to the minus st. That is always the same, times the function that you're interested in. This is dt. Okay? Okay, so this, let's calculate the indefinite integral separately, right? This is, what do you think? Integration by parts, right? Remember, s is just a constant so far for this integration part. So we have an algebraic function times an exponential function. We know, so there's I late, right? So the algebraic, this will be t, that will be our u, and the exponential dv, that will be e minus st dt. Okay, so u is t, dv is e to the minus st dt. Okay, once we have made this choice, we calculate du, which is then dt, and we calculate v, that we have the end-derivative, that is e minus st divided minus s. We have already seen this trick. Okay, so and then by the formula for integration by parts, this is uv minus integral v du, so that would be t e minus st divided by minus s. Okay, that is uv minus the integral of e to the minus st divided by minus s dt. Okay, so go on here. This is equal to, okay, let's bring the minus sign out, te minus st over s, and then minus minus, we get a plus 1 over s, and then the derivative of this thing is e minus st divided by minus s again. Okay, so this is equal to, and again we're going to do our Lucy thing by just plugging in infinity, so to speak. So, okay, what is this now become? This becomes here a minus s squared, right? And this is between 0 and infinity. Okay. What happens if I plug infinity? It is clear what happens if I plug. So now I'm going to already say again, we're going to take s bigger than 0 for the same reason as before. If s is less than 0, it's not going to be defined. So we're going to take s bigger than 0 here. I'm already avoiding any problems. So in that case, if I plug in infinity, then both of these terms are going to give an e to the minus infinity, and here e to the minus infinity. Now, this is clear. So this is going to be 0, so no harm here. The whole thing is going to be 0. But here is a little bit of a problem, because you get infinity times 0. Now you say, oh, Professor, that's 0, because anything times 0 is 0. Hey, Professor, I'm a different guy. That's not true, because any number times infinity is infinity, so it's infinity. Okay, now you got me confused. It's either 0 or infinity. What is that? Well, this is a quick review now. Undetermined form. There are a couple of undetermined forms. 0 over 0, infinity over infinity, and the particular one that we're now talking about is 0 times infinity. And if we run into an indeterminate form, what does that mean? That means you do not know what the answer is, and the answer could really be any number. Not just 0, not just infinity, it could be 7, it could be minus 3, it could be 1, it could be 0, it could be infinity. Anything is possible. That's why it's undetermined. You don't know yet. So how do you determine? Well, there are different techniques, and the one uses quite a lot is the L'Hopital, right? The L'Hopital's rule, we have already discussed this. So the L'Hopital's rule that says if you take the limit for t going to infinity, there are other cases also here, but let's just concentrate on the case that we want for infinity. That is the same as taking the limit of the derivatives. And calculate again. Okay? But provided that you get, this is for these two indeterminate forms. So if you have one of these two indeterminate forms, you can use the L'Hopital rule. So what I mean to say is, if this gives you 0 over 0 over infinity, then you can do that. But you see, to have L'Hopital, you have to have a fraction. And we don't seem to have this. What we have, so our problem is, okay, I'll do it in red. Our problem is this thing, right? We want to calculate this. Okay, I'll keep the minus st here for t going to infinity. Okay, what do we get if I plug in? I get infinity times 0, 0 times infinity. So we're getting this indeterminate form, which is not of the Laplace type. It's not of the L'Hopital's type. And L'Hopital, by the way, means hospital, and so what you need is fractions. If you have fraction, then you go to hospital, right? So what we do to solve this is fraction. We're going to make this into a fraction so that we can go to the hospital, okay? So let's do this. How do we do that? Well, we bring one of these guys into the denominator, right? And the obvious one is to bring the one with the negative exponent here, this one. This is rewriting this, and now it's a fraction. And let's see what we get if I plug in infinity. I get now infinity in the top, but in the bottom, well, 0. No. I changed the sign here, right? So it is now infinity, right? Put it in the denominator. Okay, infinity over infinity. So now we can do the L'Hopital's rule. And so that is the same as the limit for t going to infinity. And what is that? What we need to do? Take derivative of the top, which is 1. Derivative of the bottom is SEST. And if I plug in now, I get 1 over s e to the infinity, that is 1 over 0, 1 over infinity, that is 0. So even, although it needs a little bit of work, if I put in infinity in here, that is also 0. So what are we left with? So in other words, if I plug in infinity, all this is 0. But of course, I have to also to plug in 0. So this result is 0. The calculations that this is 0 is all below here, right? Minus, and remember, you subtract. Now I plug in 0. If I plug in 0 in this guy, well, that's gone. So the only thing that is left is minus 1 over s squared e to the power 0, which of course is 1. And so if I work all this out, the minus cancels, I get 1 over s squared. So a long calculation to show that if you take the Laplace transform of just a variable, you get 1 over s squared. So remember that the Laplace transform of 1 was 1 over s. Okay? So you might now say, okay, what would be then the Laplace transform of t squared? Now we can do the calculations, but at some point we're going to jump to the tables. So here I'm going to show you how you use these tables. So you look for the function, so the left is the function and the right is the Laplace transform. The table is a little bit, I don't know, it's not nicely drawn. But okay, so here, so if n is an integer, what is then the Laplace transform? Well, it is n factorial over Sn plus 1. So one higher power, and on top you get n factorial. So for this one would therefore be, so this is using the table now. So I'll put this here. Using the table, I see that this is 1 over, I said you increase the power by 1, and here you put the factorial of the exponent. So it looks a little bit like the power rule, but it really is not. And don't try to make too much of it. It's just a new rule. Okay? So let's just, for the fun of it, what is the Laplace transform of t to the 5th? Well, it's 5 factorial divided by s to the power 6. And so once we have this, it becomes very... Now, you shouldn't memorize these things. First of all, it's an open book, but even if it would be not an open book, you would always be able to use the tables. So you use these tables to calculate these Laplace integrals, unless I explicitly ask you to show the calculations of a particular Laplace transform. Okay, moving on. Let's do another one. Again, I could use the tables here, but I'm going to still do the calculations, just so that we get a little bit used to this. Well, there's two things involved, right? Improper integrals and in the undetermined forms. That's also kind of part of this whole game. All right, so what about the exponential function? And just to do the whole bit in at once, I'm going to take not just et, but e8 times t. Okay, but we have seen so many times that these things appear in our solutions, in our solutions of differential equations, right? So this a would then be the real part of the etc. Okay, remember that how these come. Okay, so we're going to link this to differential equations, but not in this lecture, and that's part for the next one. Okay, but for now we're just talking about Laplace transforms. Okay, so let's write down again. The Laplace transform of EAT is, well, 0 to infinity, e to the minus st times this function, EAT dt. Oh, okay, but that's something, when I see something like that, I like to simplify this, right? This is just one e, because I can add the variable, so this EAT minus ST dt. So in fact, if you want, a little bit unorthodox way to writing it is this way, right? Let's keep the minus sign here, dt. Now, what do we know for this thing? We knew that we have actually done the calculations here, right? Here this was all the way in the beginning here. We know that the antiderivative of E minus t is this guy, okay? So what is the difference now? Instead of an S, we have an S minus A, right? So we have not, here's E minus ST, we have here E minus S minus A t. So just replace S by S minus A, Okay, just replace s by s minus a. So this is then equal to 1 over s minus a. Let me just do it the whole way through. Okay, so in this whole calculation, the only thing that changes here, let's see, the only thing that changes is the s becomes an s minus a. So I should put s minus a here, s minus a, s minus a, up to here, you replace s to s minus a. So that's the only thing you're doing everywhere, replacing s by s minus a. You can do the details of it, but it's pointless, right? It's the same thing. So you get here 1 over s minus a. So this one, as I said, I'm skipping here the calculations because I've done them, and I just replace s by s minus a. So we have here that EAT corresponds to 1 over s minus a. By the way, what happens if a is 0 in this formula? Then AAT, what is e to the AT? That's just 1. And then on the other side, we get 1 over s. But we did that, right? This actually was what he proved here. This calculation was exactly that. So again, that's where these things come from, right? So this is indeed true. For a equals 0, we knew this already, and now we just copy the calculation, and we see that's what you get. So it is a little bit surprising, the things, right? That you get these kind of changes. And before I go any okay, so I'm going to do more examples, but I think it's, since we have seen this now, I want you to understand why is this happening. And so this is called the shifting theorem. It's called the first shifting theorem, but let's not bother about that because we're not going to look anything else, work at everything else. So if we have like a situation like this, what this means, so remember, this is a function and this is Laplace transform, okay? Then we can, from this, we can find the Laplace transform of the following guy. So if I multiply with e to the power at, the effect of multiplying on the original function, and in the Laplace transform, the effect is quite surprisingly a shift. Why do we call this a shift, by the way? Well, that is just because if you graph this function, right? So if this function looks something, this function looks something like this, so this is say capital F. What is this shift then? That means that we shift a units to the right. Okay, so if this is a, then the whole thing is shifted, so the whole thing, the whole picture would then be shifted like this. That is that's what this function then represents. Graphically, it corresponds to just shifting the graph of the original function. So that's why it's called the shifting theory. But notice, this is not what happens on this side. On this side, it is really kind of dramatic. We multiply it with EAT. Why do I mention this here? Well, look at what I just said. 1 corresponds to 1 over s. So, by the shifting theorem, if you multiply 1 by EAT, then you shift this guy, and you get this guy. So again, so the fact that you get this from that follows, said it differently, this follows from this using the shifting theorem. But of course it's just calculation, right? It's a theorem, it's always true. Okay? So therefore from the shifting theorem I can now say what is E 5t t to the third. Let's think about this. What is this? Well, what is t to the third? From the tables, so here, when I'll indicate each time I use a table, we know that this was, you have to take the factorial divided by the higher power of s. Don't forget that this is a new variable, right? Don't write t here, s to the fourth. Now, what from the shifting theorem, so this is shifting theorem, this tells us, well, you take this result that you have here and you shift it by 5. So we get 3 factorial over s minus 5 to the power 4. Okay? So, by the way, these things are even listed in the table here. So, for instance, where is this? I saw it somewhere. But yeah, here, of course, this is just the shifting theorem. That's, but I thought it's actually explicitly. Here is explicitly. Okay. So it, in some sense, this one that I just circled is not necessary to put in the table because you can get it easily from the shifting theory. Okay. Good. So this is a way of finding, with the shifting theory, you can now easily find many other guys. All right. I want to still do some more calculations, and this is a little bit trickier calculation in some sense, but it actually is not so bad. So let's calculate I want to do this for sine omega t and cosine omega t. Again, I'll use omega as my frequency. We have seen this very often happen, right? So we want to find here the Laplace transforms of these two guys. And there is a reason that I'm going to do both at the same time. Sometimes in mathematics, just doing one single problem might be harder than doing a bunch of problems together. And you'll see here why I say this. So, okay, let's for the moment call them, I'm going to give them some names, S of little s and C of lesser s from sine and cosine. In the book they use F and G, but I think it's more telling if I write an S and a C here. I don't know what they are yet, but that's the whole point. So let's write down what S of s, what this should be. Well, by definition, this is 0 to infinity, e to the minus st times sine omega t dt. Okay, and what is C of s? Well, C of s is the same thing, but now with the cosine. E to the minus st cosine omega t dt. Okay. So how will we solve these integrals here? So let me write the integral again. E minus st sine omega t dt. How do we find the antiderivative of this function? Well, this is again an Eilate problem. You might have seen it or you might not have covered it in Calc 2 because it's kind of a little bit of a nuisance, the calculation. I kind of never cover it, but because the calculation is a little bit complicated. But now we'll see actually it won't. Because, okay, it's Eilate. Why is it Eilate? Just convince ourselves of that at least. Well, Eilate means you have to have an exponential. This is an exponential, this is a trigonometric. Trig and exponential. Okay, according to Eilate, the trig should be u. So u is sine omega t. And then dv is e minus st dt. So from that we see that du is omega cosine omega t dt. And v is e minus st, don't forget, divide by minus s here to compensate. Okay, so by the chain rule, this is uv minus integral v du. That is uv, that is sine, it's e minus st sine omega t divided by minus s minus v du e minus st minus s times du, which is omega cosine omega t dt. Oh, I'm running out of space here, so let me try to move this a little bit. I'm not sure that it's going to work well, but okay, all right. So let me write this a little bit better now. Omega cosine omega t dt. Okay. What's the problem? The problem is that we have. Normally this becomes simpler, and it didn't really become simpler. It just, instead of a sine, we have a cosine. Now this omega is harmless, and this s is harmless because it's just constant. So it actually is actually this guy. So one transforms into the other. Well, that's as far as partial integrations is concerned, and so what one normally does is do another partial integration, etc., etc. But we'll skip this a little bit because we'll say, okay, so let's now use this and plug this in, and let's find calculate the improper integral. So what happens here? So let's calculate first this. Let's calculate this guy. Sorry. So I want to calculate this e minus st. Well, we have a minus here, so I'm going to from the s in the denominator, right? Sine omega t over s between 0 and infinity. So what is this? If I plug in 0 and infinity, right? This I would have to evaluate, and then so what I'm trying to say is that this improper integral is this guy minus this improper integral. Well, with this omegas and s's in here, we have to take care of these guys, but basically we're related to that. Okay, so let's see, what is this here? What do you get if you plug infinity? Well, you get infinity, and again, s is positive. Sorry, I should have said that from the beginning. S is positive here. So if s is positive, then if I plug in infinity, I get e to the minus infinity, which is 0. Now, what is sine of infinity? Now you say, okay, sine of infinity doesn't exist because sine is the limit for t going to infinity of sine does not exist. It's not that it's infinite; it doesn't exist because sine sine goes up and down, right? So it never goes anywhere in the limit. It's oscillating. However, it's always bounded by 1. Okay, so we know that this is at most e minus infinity minus e minus infinity over s. Because this is at most 1, okay, right? So, but this is 0. So this is a positive, this is, well, I should perhaps take the absolute values here. So let me put it this way. If I take the absolute values of these things and I plug in 0 infinity, then this is less than that, which is 0. So this is actually 0. So what I'm trying to say is, another way of saying this is that the limit of an exponential decay times a sine. We have done this actually before. We've seen this when we discussed steady states and so on. We said, okay, if you have something of this kind, that actually goes very quickly to 0 and in the limit, right? So the limit is 0. Okay. Well, that is if I plug in infinity. What do I get if I plug in 0? Okay, so should be careful, right? Sorry. So let me go back here. I'm doing away with the calculation and just saying what we get. Sorry, let's start over again. So what we get is, okay, let me write it up again. If I plug in infinity in this function, I get 0 minus, and now I plug in 0 so minus e to the 0 sine 0 over s. Well, this is also 0, so the whole thing is just 0. Right? So what have I said now is that this thing, well, that is, you put 0, you take the endpoint 0 infinity for this guy. The first term is just 0. What's the second term? Well, I have an omega and a minus s. So that is plus omega over s, right? I factor this out, and what I'm left with, so if once I've factored out this one and this one, what I'm left with is exactly this guy. So I get cs. So we see that s of s is just omega over s cs, okay? So let's now see what happens with the other one. Let's do the same thing with c of s. So c of s is this integral e minus st cosine omega t dt. We do exactly the same. So u is cosine omega t, and dv is e minus st dt, right? We're going to do again partial fraction. So sorry, let me just do the partial fraction first without the endpoints. Okay, and then we put in endpoints. Okay, so this is du is, now be careful, there's a minus sign, minus omega sine omega t, and v is e minus st divided by minus s. Okay, that's just before. So this is uv, so this becomes cosine omega t e to the minus st divided by minus s minus omega, minus again, no, sorry, what is it? V du. v du. Yeah, minus omega sine omega t e to the minus st divided by minus s dt. Now, again, we recognize that apart from these two guys, what we get here is the sine, the corresponding integral for sine. So we do the same thing. We're going to plug in the endpoints now. If I plug in the endpoints, 0 and infinity, here, this will give me just basically up to this constant here, the Laplace transform of the sine. What does this one give me? Okay, so let's calculate this. So we have to calculate cosine omega t e to the minus st over minus s between 0 and infinity. So we have to plug in infinity and we're back to 0. If I plug in infinity, what do I get? Minus, so here, what do I get if I plug in infinity? Well, for the same reason, because cosine is bounded in absolute value between minus 1 and 1, whereas this exponential is going to 0 very fast, this whole thing is just 0, for the same reason before. But what do we, now be careful, if I plug in 0 in this function, it's not 0, because the cosine of 0 is 1. What I get is minus 1 over s, okay? This e to the power 0 is 1, this minus s stays what it is. Remember, we always plugging in t. And this is cosine of 0. So we get 1 over s. So what we see here, that this is the same now as, well, we do the same thing. This one, if we plug in the endpoints, I get not 0 this time, but again 1 over s. And if I plug in, and if I factor out minus omega s over minus omega over minus s, then I actually get in total that will give me a minus sign, right? So I get minus omega over s, s of s. Okay, so let me write up what I get. We find that s of s, the Laplace transform, is equal to, of the sine is omega s times the Laplace transform of the cosine. And then vice versa, the Laplace transform of the cosine was 1 over s minus omega s, the Laplace transform of sine. Did I copy everything right here? Just double checking. Where is this here? 1 over s minus 1 over s. Okay, okay. So I'm just copying these two things, right? So let's now solve. So in other words, let's plug this in here. We get this is omega s times 1 over s minus omega s, capital S. Okay. So I'm replacing capital C by capital S. Let's forget about the little s here now. Don't have to write it all the time. So we will get capital S is equal to omega over s square. I'm expanding this. Minus omega square over s square capital S. Let's solve for capital S. Bring this to the other side. So S is 1 plus omega square over s square. I brought this to the other side, right? And then comes a plus sign and then factor out s equals omega over s square. So we see that capital S is equal to is equal to omega over s squared divided by, no, we can put this on common denominator. So this thing is just s squared plus omega squared over s squared. So it is s squared plus omega squared over s squared. So the s squares cancel and I find that capital S is equal to omega over s squared plus omega squared. And what is capital C then? Well, capital C, we have this relation between them. So we have to, so capital C is S over omega times capital S, right? Cross multiply, bring this guy to the other side by taking its reciprocal, multiply with the reciprocal here. So we capital F is this, and we just found that this is S omega times omega over S squared plus omega squared, which simplifies as S over S squared plus omega squared. So let's write down what we have. If we start with sine omega t, then the Laplace transform is omega over s squared plus omega squared. If we start from the cosine omega t, it's almost the same except instead of an omega, we get an s there. So this is also a little bit strange. Sine and cosine seem to always have behaved kind of similar, right? They were really almost, they were like cousins, cosine and cosine, right? But if you see Laplace transform, it's a little bit different because this has a constant numerator and this has not a constant numerator. So in the Laplace transforms, they do look different. Okay. So let's now see whether we can we find the Laplace transform of e to the minus lambda t cosine omega t. What is that? Well, we're going to use the shift theorem. With the shifting theorem, we take the one for cosine, which is so s over s squared plus omega squared, and then we shift by this coefficient. Now, be careful, it's a negative. So this means we replace s by s plus lambda, s minus minus lambda, okay? So with the shifting, we have to replace, so this is not correct, right? So I have to shift now by replacing, so I have to replace, oh, that is, you cannot read that, right? Let me, okay. So this is not correct. We have to shift. So let me erase the s's here. And this has to be now s minus minus lambda. So so we see that e minus lambda t cosine omega t will be s plus lambda over s plus lambda squared plus omega squared. And sorry. I write equal, that's not equal, right? Be careful, don't write this as equal. I made that mistake here, but that's wrong. I should write this double arrow here. Cosine omega t corresponds the Laplace transform to this. And then similarly, what is this then? Well, again, you do the shift of the sign, which is now, well, top nothing happens, but in the bottom we have still this guy. Okay? So again, these are also in the table, but it's not necessary because where are they? Say here. Okay, here they are with positive lambda, so that's why they subtract, but I had the negative lambda. So okay, so I want to do one more example because it will also explain one more property that is very important for us. Let's find the Laplace transform of the following function: cosine hyperbolicus omega t. Cosine hyperbolicus, cosine or hyperbolic cosine. Yeah, sorry, I'm always used to pronounce it so, but it's hyperbolic cosine. What on earth is this? Well, it's just a fancy name for a function that you can write down very easily. Sorry, I have to always check because I'm not used to using it that much, so I always have to double check the cosine hyperbolic is, okay, that is equal to, by definition, so this is just the definition. This is e to the omega t divided by 2 plus e to the minus omega t divided by 2. It's just a sum of two exponentials, one with the positive and one with the negative. Of course, I can put this on one common denominator, so it's more commonly written as this way. And I think the hyperbolic sign is the same, except that there's a negative sign. Instead of adding, you're subtracting. But I don't know this. Let's not talk about too much. So how do we find the Laplace transform test? Now, of course, you could very well do the general calculation just by definition. But let's think a little bit about this. This is basically the sum of two functions, right? So what happens if I would take the Laplace transform of two functions? Let's just think the sum of two functions. Well, by definition, this would be e minus st f plus g, and this is from 0 to infinity, right? That's the definition. But dt. But we know that for integrals, they are linear. We can split them. So we can split this as 0 to infinity e minus st f dt plus 0 to minus infinity e minus st g dt, because just expand and then split. And this is just the Laplace transform of f by definition, and this is just the Laplace transform of g by definition. So in other words, the Laplace transform of a sum is just the Laplace, you take the sum of the Laplace transforms. Moreover, if I take a constant multiple, say c a times f plus b times g, so af plus bg here, a and b are constants, well, again I split, but since they are constants I can bring them out. That's what constants do, right? So I can take the, oops, the wrong one, take the constants out, and so this becomes just that. So we see that the Laplace transform of a linear combination is just a linear combination of the Laplace transforms. All this to say that to calculate the Laplace transform of the hyperbolic cosine of omega t, well, you just take the Laplace transform of e omega t plus half, the half comes out, the Laplace transforms of e minus omega t, okay? And we know what these are. This is a half, well, you could even think of it as the shift theory, but this is 1 over s minus omega plus a half 1 over s minus omega is plus omega. So I'm using here, let's go to the table, but we have done the calculation before, right? So here we see this, okay? Okay, so this is what we get. Sorry, okay, here we are. Now, sure, nice, but it's actually nicer in some sense, because let's put everything in common denominator. Okay, we get a half. I'm going to multiply this with s plus omega, and this also plus s plus omega, and then here I have to multiply with s minus omega. So we were trying to write everything on common denominator. So we get a half s plus omega plus a half s minus omega over s minus omega times s plus omega. Okay. Now, what is the top here? Let's look what happens in the top. We have a half s plus a half s, that will be s, and we have a half omega minus a half omega, so that's gone. So we get s. How do we get in the denominator? That's a double product formula. We get s squared minus omega squared. So that's much more compact, right? So you see that the Laplace transform of the cosine, the hyperbolic cosine, is just s over s squared minus omega squared. Again, this is also in the tables. Here they are. Okay, and you see for the sine, it's kind of again similar thing happens as with the cosine. Instead of the s, we have now a b on top. But again, I leave that calculation for you. So let's see. I think I covered everything that you need to know for the homeworks, and yeah. And so in the homeworks, depending on whether they ask, they sometimes say you can use the tables, sometimes they say you have to do the actual calculation. So do whatever what it says. Now, there's also a theoretical part here that I'm kind of glossing over all the way, is when do these things exist? So I don't want to say much about this. And in fact, I'm going to skip the problems that refer to what's called piecewise continuous. So piecewise continuous function, what is that? So continuous function is a function you can draw without lifting your pen. What is a piecewise continuous? Means you can draw it, but at some point you have to lift, and another point you have to lift again. But you do this only a couple of times, finely many times. If you do it only finely many times, then it's called piecewise continuous. Okay, so there's like a couple of jumps, but that's it. And a function that satisfies this has a Laplace transform, provided also that it doesn't grow too fast. So the function has to go what's called at most exponential. I don't want to say too much what that means, but if you think about if you want to think like very generally, it means it kind of lies underneath the graph of an exponential function. Okay, if there's an exponential function, if you find an exponential function that lies above it, then you are dealing with a function that any function that is of this form that lies on the next. So this red one is supposed to be an exponential function. Any function that lies on whose graph lies underneath of it and it consists of finely many pieces, continuous pieces, such a function has a Laplace transform. And you can calculate Laplace transform in that case. So I'm just going to do very quickly one example, because I don't want to spend much time on it. Suppose we have the function ft that is defined piecewise, and piecewise definitions are very often given this way, right? You say from 0 to 1, that's how it looks like, and then from 1 to t to infinity, all the rest, it looks like minus 3 e to the minus t. Okay? So let's see what happens if we calculate the Laplace transform of this guy. So this would be 0 infinity e minus st times this function, ft dt. Now, how do you integrate a function that is given by different formula depending on where you are? Well, you split the integral, the integration interval accordingly, 0 to 1, e minus st, and so on this interval it's just 1, and then what's it on the other interval? From 1 to infinity, it is e minus st times minus 3 e to the minus t dt. Okay. Now, each of these integrals, we know what they are. They are e minus st over minus s between 0 and 1. And this would be, this is multiplying. Yeah? We can bring the minus 3 out. So, plus, sorry, I don't know why I wrote minus here. Plus, we have a minus 3 that I factor out. And this can be combined in e minus s plus 1 t. Correct? Right? Just combine the two exponents. And so this is then e minus s plus 1 t over s plus 1. And this is between 1 and infinity. Now be careful. You say, oh, okay, professor, this is just a Laplace transform of this guy. No, because this bound is not 0, it is 1. So we have a different endpoint here. So what this means is, okay, let's plug everything in. If I plug in 1 in this function, I get e minus s over minus s, minus, now I plug in 0, that is 1 over minus s, plus, or minus 3. And what do we get here? If I plug infinity, we know that if I plug infinity, again, s is supposed to be positive, we get 0 on top, s plus 1, of course, it doesn't matter now. And if I plug in 1, I get e to the minus s plus 1 over s plus 1. And that's it, okay? So what we get is that a couple of terms left now all of a sudden, right? So we have e to the minus s, minus e plus 1 over minus s, that's the first one, and the second one is plus 3 e to the minus s plus 1 over s plus 1. So you see that this thing is no longer such a nice formula anymore, right? So Laplace transforms of these piecewise continuous functions can be much more complicated, and we cannot get them just from the tables. That's why we're not going to cover them. I just wanted to show you that you can do it, but I'm not going to bother with those again anymore. Okay.